Out here. So today we are making glass. The glass has been baking out here overnight or incubating. So this is at 1150 degrees. So very warm. I'm going to go ahead and bump this up a little bit so that while we're talking we can get an extra 50 degrees. We're going to cast this at around 1200 today. What I noticed in the spring was that our glass looked a little bit more viscous than it did the previous years. We recently transitioned from this furnace, which you can see is a battle tested. It's got some heating element issues and I can't find replacements. So I'm either gonna have to scrap it or make my own elements. So got to figure that one out. I usually like to have some backups, which is why I'm still thinking of that one. But still dialing in that temperature. So we're going to bump that up. It should be ready to go here in a few minutes. But first I want to talk about some of the relevant background for what's happening in that crucible. So last week we chose a recipe. We put in a glass former, which is silica. We put in a flux, sodium carbonate. We put in a flux stabilizer, calcium carbonate. Some of you put in some aluminum oxide, which is a stabilizer. Some of you put in borate, which is or a Gerstley borate, which is a melting agent, or it's essentially a flux, but it's kind of like riding the fence between a lower melt temp glass former and a flux. But that should make the viscosity go down in theory. So what exactly has happened now that we have heated that up? Well, if we walk through the process of making glass from a chemical point of view, this is what things would look like. So quartz is what our sand is made out of. Now, quartz can make quite large crystals. These are probably from Arkansas. There's some large quartz mines down there where you get these giant spears of quartz. Once you crush that up, it looks white or sometimes a little bit off-white, depending on if some iron is present. So we have varying degrees of purity of quartz. But sand, of course, has very small grains compared to what we just saw. Well, if we were to look at it from a chemical point of view, it's SiO2. Now, that doesn't mean it's like H2O, where there are 2 oxygens and 1 silicon in this little chunk that's like flying around in the air like water vapor would, or making a liquid. This is a formula, not a molecule. Maybe we've never appreciated that difference. A formula tells you a whole number ratio in a system that's bonded, many times to other neighboring atoms. It's a formula weight, not a molecular weight like H2O, which you can actually get a single molecule. The bonding motif is that every silicon is bonded to 4 oxygen, and every oxygen bridges 2 silicon. So you see that 4:2 bonding ratio simplifies based on, whole number ratios to 1 silicon for every 2 oxygen. But you can see that just based on the bonding habit. So this is what it would look like if we could see perfectly the atoms that make up that silica crystal structure. And this would be true whether it's sand or purified silica or the Michigan lakeshore silica or Mason sand. It's all the same material. So here's that close-up of what's called the silicon tetrahedron. So it's called a tetrahedron. We'll talk a lot more about that shape, but it's 4 triangles that are making a 4-sided shape. And that 4-sided shape with 4 faces, we're going to call a tetrahedron. So the bond angle is similar to carbon. It's basically the same as carbon if it was methane, but in this case, silicon dioxide. So in some book representations, you will see a reduced representation where the silicon oxygen tetrahedron are just shown as tetrahedron or tetrahedra. So in this diagram, we're to assume that at the center of every tetrahedron is a silicon atom, and all the bridge points between two adjacent tetrahedron are oxygen atoms. We're not going to obsess over all the history of shorthand in the glass-making industry, but it's fairly common to see these types of diagrams, and so I just want to point that out so that we understand what's happening. Well, that's silica, that's the glass former. So how do we get that to become a glass? Well, in the last chapter, we looked at percent ionic character. And we identified that some bonds are quite low in ionic character, and by counter argument, by default, that means they're high in covalent character. And some bonds are very high in ionic character. So covalent, ionic, well, look where silicon dioxide is. Distinctly in the middle. It doesn't quite know. Am I covalent? Am I ionic? I'm certainly polar covalent, right in the middle, but this means it's going to have characteristics of both covalent bonding and ionic bonding. Well, when it's all by itself, silicon and oxygen together, it knows exactly how to form its crystal structure because this is the most efficient way to pack silicon and oxygen. But what happens if we add ionic impurities? Well, it messes everything up. This is a simplified diagram, a real oversimplification, but I want to show mechanistically what happens to the bonds first. So in that previous picture where there were hundreds of bonds, we're going to pick out a single silicon-oxygen-silicon bridge to think about what could happen, okay? That's all we're showing here. One of billions in the system, a silicon-oxygen-silicon bridge. Well, when we add a ionic compound, specifically sodium, potassium, lithium, calcium, magnesium, the ionic character of the alkali metals is going to mess up the bonding of the silicate. Now you might be thinking, well, I thought we put in sodium carbonate. You did. And at around 800 to 900 degrees on the way up to its current temperature, the carbon and two oxygens from the carbonate, Na2CO3, that's washing soda, sodium carbonate, the carbon dioxide left and outgassed. That's a process called calcining. We calcined that and we removed the carbonate. So last night, when I was doing the thermal ramp for the furnace, once you get up around 1,000 degrees, you can actually hear bubbles popping in that furnace because the surface skins over with glass and it's still blowing carbon dioxide bubbles from the reaction that leads to sodium oxide. So the carbon dioxide bubbles, I had a crucible that actually had a glass bubble forming on top, and then it pops, and it's kind of like boiling potatoes, you know, all that kind of a foam you get on top that sort of builds up. It's kind of like that. Or enter your favorite boiling over story. But the idea is to keep enough space in the crucible to prevent it from actually boiling over, because that makes quite a mess in the furnace, because it's glass, after all. Regardless, we off-gassed the carbon dioxide from both the sodium carbonate and calcium carbonate, so we're going to be looking at how the oxides behave. So the sodium oxide at high temperature, when it gets close to these types of bonds, something interesting can happen. The oxygen, the O2 minus from the oxide, is able to reform a new bond with a particular silicon. This is showing one electron events. So remember, each bond is worth 2 electrons. Well, if one electron goes this way, and one of the electrons that was a charge on this oxygen goes this way, well, we can form a new silicon-oxygen polar covalent bond with the oxygen delivered from the sodium. You see what happened? So this is now called a pennant, dangling oxide. And so this is a unique case where it has a -1 charge because this charge is now bonded polar covalently to the silicon. And so now we've got one of the sodiums bonded to this oxygen, and the other sodium, not bonded, well, ionically bonded, ionically associated with this oxygen. And you see we effectively snipped this bond and now interposed two sodiums. You follow what's happening here? We're busting up the covalent linkages that previously existed between every silicon, oxygen, silicon, oxygen, silicon, oxygen. Well, if we start messing up all those bonds, well, it's no longer going to be a crystal structure. It's going to turn into a glass that's going to behave in many respects like the parent crystal structure, but now it can no longer crystallize because the bonding regularity has been interrupted by all the ions. And we put in a lot, 90 grams of silicon dioxide, 50 grams of sodium carbonate, 25 grams of calcium carbonate. That's going to severely mess up the silica crystal structure. The calcium story is similar, but remember, we call this a flux stabilizer. The name flux in this case just refers to something that causes a substance to melt at a lower temperature. There's other contexts where you may have heard of flux, like you're fluxing metal before you solder. You may be in physics and you're thinking about a flux field of magnetic field lines through a loop of wire, or an electric field. What's the flux, the field flow per unit? There's all these different definitions of the word flux. Well, in glass making as well as metallurgy, we flux the gangue in a blast furnace with iron ore. That's this context. We flux the bonds in the silica with sodium and calcium fluxes to make them melt into a glass. That's the context. Well, the sodium is just a flux, where calcium is a flux stabilizer because calcium is a 2+ ion. So instead of having two sodiums and an oxygen, we have one calcium and an oxygen. The story looks a lot alike. The oxide temps this bond away, forms a new bond, breaks this bond. We end up with two pennant oxides. But now the calcium, because it has a 2+, can sit in between those and still form a association where the previous bond was. Now that's going to migrate. This is actually a dynamic process where bonds are broken and reformed as the glass melts and flows. But the calcium still dwells some of the time linking two pennant oxides, which has a stabilizing effect. It still fluxes it, it still messes up the bond, it still turns it into a glass, but it still stabilizes it and makes the glass a bit stronger, a bit more resistant to attack by water. Some glass, if it's too highly fluxed, will spot and actually get cloudy over time. Calcium and even aluminum can help arrest that process, slow it down. So we've disrupted the bonds with ionic impurities, a flux and a flux stabilizer. So these cartoons here from the Callister text show kind of what that would look like, not quite drawn to scale, but the high regularity of the parent silicate is interrupted with our ionic centers there, the sodium ions. They're still tetrahedra. This would be a little tetrahedron of silicon and oxygen. So locally they still look kind of similar, but the long range order is no longer transposable. You know, that this is a transposable crystal structure. That breaks down, no longer the case. Now we also put in a bunch of, or any questions about the basic structure of glass? Does the story make sense? It's kind of intuitive, hopefully. When we added our different metal impurities, we obviously changed the optical appearance. Silicon and oxygen and sodium and calcium themselves don't absorb in the visible spectrum. So that makes clear glass much the same as window glass. That's pretty much the batch type that we're making here. But by adding in those metals, it changes how it absorbs light. The way that works is that instead of a silicon sitting in between 4 oxygens, these metals will sit in positions in the glass between 4 or 6 different oxygens and make a coordination center. What's a coordination center? Well, it's a metal that's holding on to 4 or 6 oxygens at the same time. And that has a unique ability to absorb light depending on what metal is there. So in other words, copper oxide is going to make this bright blue. Well, that means it's absorbing in red and orange. And that's going to make it appear blue because it absorbs the part of the light that we don't see, and we see the color based on what remains. So it's a game of complements, and we'll talk a lot more about that in lecture. Roy G. Biv. Well, if you take out Roy, you get Biv. And so that's why we got the blue, indigo, and violets represented in some of these. Conversely, if you have and red's a difficult color, but let's say we end up with some greens and purples, it's all just subtracting parts of the spectrum and we see what's left. Some of these are hard to produce. I've tried making these and been mostly unsuccessful. Stained glass from windows and cathedrals and such, the red is often caused by gold, small microscopic gold particles. But some of these are difficult. Some of these are kind of somewhat toxic, uranium, fluorescent, yellow-green, that'd be awesome, but still kind of a hazard to work with. So we chose a selection of these and doped that into our glass batches. Now, just to make you aware of what's, this isn't your batches, but these are kind of what it looks like, obviously. This is before I got into all the exotic sand, different sand materials. This is with purified silica, shaped it into a little volcano-looking structure there. So it melts nicely, but that, of course, got loaded in the furnace. And that's the old furnace there. And it's been baking for about 12 hours, 12 and a half hours. It was up to temperature at around 11 o'clock. And it has been at that temperature ever since. So what we've got to fill out here today, this story is shown in the lab. We've got this plot here, and this is showing the relationship between viscosity and temperature. Now this would be for a really low melt temp glass, like a highly fluxed lead glass. And so viscosity is thickness of the pore. And so low viscosity is like water. It flows very easily. High viscosity, corn syrup, peanut butter, grease, those things are much, much higher. Well, for every particular glass composition, this part changes. Its melt range changes depending upon the identity of the glass forming parent crystal and the degree of fluxing. But the overall curve and the way it softens as a function of temperature is really identical. So that softening range is dependent upon all the different factors, such as the identity of the flux, or whether it's a high boron content, that's lower melt point, or a high silica content, that's a high melt point. So there's some questions that you'll have to read through and gain some understanding of how this process works. In particular, there's a question about lithium and sodium and potassium. Well, lithium is a more effective flux than sodium, and sodium is a more effective flux than potassium. So let's imagine that this range was centered on 1200, our pore temperature today. So let's imagine this was 1200 and this was the viscosity at which we poured. Well, if we had a lithium glass, the curve would shift in this direction and our viscosity at 1200 would end up lower because it's a more effective flux. And so you just take this and drag it this way. If this was sodium, we would then add potassium as a replacement for sodium, and it would take this curve and shift it up this way, which would cause our viscosity to then be higher using that flux. Can you kind of see how that would work? We're shifting this curve based on the identity of the substance present. And that particular set is a pretty typical way of controlling that. And your viscosities during the pour would look different. So this is simulated data here to show what a low, medium, and high viscosity glass would look like during the pour. And we're going to pour them all there on the plate, the metal plate. So keep an eye on the thickness of the pour. And I will have a video rolling on it so you can review back to answer questions later. It's easy to do, so why not? I've also got some representative pictures. So these are the standard compositions that we're going to be conceptually comparing our glass to. We used to pour nearly the same set year after year. Well, then I started mixing things up a bit, and instead of me telling you exactly what to put in the crucible, I set ranges, and now it's different every year, which is good and bad. The good thing about it is it's always new. The bad thing about it is it's more unpredictable. But that's also kind of good. So for the questions that ask about the standard sodium glass, well, that's this one. And you can see the approximate size and diameter. And so this was a high flux, this was a low flux with everything else held the same. Okay, we can see some differences here. The diameter is smaller. That means that during the pour, it didn't spread as easily, higher viscosity, and I probably didn't recover quite as much from the crucible. Another fingerprint of high viscosity. So we're going to try to relate, since we're not actually doing viscometer measurements on the glass, we're going to be trying to relate some of the remnant artifacts of the pour to viscosity. And so the diameter of the glass disc becomes a pretty good way to semi-quantitatively or qualitatively assess the viscosity during pour. High flux, low flux. Here's an example of lithium versus sodium versus potassium. So lithium is a smaller ion, it's a more potent ion, and it moves faster. So for the same molar concentrations of our fluxes, 0.46, 0.46, 0.46, the lithium will be more active, and this one cracked, of course, but you can see that it's spread out to a much bigger disk than the sodium did, and at the same pour temperature, the potassium was a smaller disk. So much more sluggish to pour, high viscosity. This poured surprisingly quickly, not quite like water, but kind of like pancake syrup, maybe thicker than pancake syrup, but you get the idea. So try to get your mind wrapped around the relationship of the disk size as a fingerprint of the viscosity during the pour. So you can refer to these images to answer the specific questions since we're not pouring those. Another reason we don't pour these anymore is lithium is such a potent flux that it actually is very damaging to the inside of the furnace. That's part of my problem here. So I've fluxed with lithium. If you look here at the top element of the furnace, you can see that it's cracked and caving in. Well, the ceramic in a furnace is also ceramics. It's silicates and alumina and zirconia. It's also susceptible to fluxes. So if you have fluxes that are able to vaporize, they actually embed in the brick, and because that one is bearing its own weight, it's not like it's load bearing for the furnace, but it's bearing its own weight, it actually droops and sags. And so lithium, you got to be careful. It's a fairly potent flux that can soften the brick in your furnace. Potassium, on the other hand, is such a tight flux at our pour temperature. I really should be pouring these at like 1400, but when you pour potassium at 1200, it has so much tension left when it cools, they almost always explode. Okay? So now by explode, here's what it looks like. And there probably will be a few that do today. So it's not like a grenade that like goes off like this. You know, that's not what to expect. It's tension in a disc. And so the way that that explodes is that it cracks and goes in all directions, but then follows a parabolic arc that is more likely to hit you in the legs with just little glass shards, chunks of glass. And so that's what you expect. You kind of hear this like snapping sound, and then it goes in that direction. I can usually tell glasses that look stable or not stable. We'll talk about that. It varies year to year, but don't be surprised or too surprised if we have some that do that. That's why safety glasses, safety goggles are important, but usually the glass shards are, you know, that area. So, a bit more introduction today, just because a lot of what we're doing today is observation and some measurement. So you can see some various glass compositions that we kind of patterned our batch range on, but here you can either just attach or your batch record from last week. I've got those up here front and center. You have your descriptions, answer some questions about that, stabilizers, and then we've got this table here. We all use sodium flux today. Didn't really use the other two because of those challenges. Viscosity rating, you can say lower or higher. You can rate them 1 through 5 or 1 through 10. It's kind of up to you, but try to come up with a semi-quantitative way to rate viscosity. The diameter of the glass discs will have basic rulers. Some people like to use their own calipers. That's also fine. But to the closest millimeters, probably all you need. Whether or not it shatters, that of course can make the diameter measurements a little bit of a challenge depending on when we take the measurement. But you know, if it shatters, it's no big deal. Put a dash, describe what happened. So this is more of the physicality of the glass that we made. And then there's another table with ion concentration. This is talking about the dopants that we added. And to assist you in this process, I did post a spreadsheet. This spreadsheet is in Canvas. And so just to help you see what's going on, hello. Not really letting me scroll. I see what's going on. Okay, so let's just pick a composition. Let's say we're picking on A here. So we've got the silica, sodium carbonate, calcium carbonate. These are generic chemical names. They're not specific to the type that you use, but this gives you the batch mass. And so this, we added 0.49 grams of copper oxide in batch A and a little bit of aluminum oxide. So with those inputs, we can then calculate what our total fired batch weight would be and the final percentage of copper in that glass. So that's all found over here. And this is already populated. Double check the math, you know, because I was looking at the handwriting. I think I got it all transposed right. But the PDFs of these are also there posted in Canvas. But this is where you can look to get your metal percentages. That way we can relate, this is around 0.3% copper in glass, and then that gives us a certain color depth. And we can see copper glass and low cobalt glass and a medium chrome glass. And for composition D, never got the batch sheet, so you know, see me about that. We'll try to get that on the list, take a picture of it for whoever's D. If you happen to have that, we'll need that here in a minute. So this is on Canvas. That will help you out with these questions. So that will give us all the relevant background we need for those questions, and then we wrap up with a couple of questions about safety glass and this kind of very odd sounding construct called Prince Rupert's drops, which, you know, what is that? Is it a throat lozenge? What is this? Well, it's the name given to these interesting glass blobs that, when cooled quickly and you probably, maybe you've heard of it, when cooled in water, has ridiculous tension. You can shoot it with a gun or rifle, and it will actually split the bullet and not break. But if you just nip the end of this tail as it's strung into the water, then the whole thing explodes, and that one does go off like a grenade. And so you may have heard of Smarter Every Day. He did a whole expose on it, and it's a novelty in this context, but it is what is used for safety glass for cars, showers, construction pieces. Some of them are even weight-bearing. It's kind of surprising all the places that stress glass or hardened, the heat-treated glass can be applied in different applications. So, you know, watch some of this, put down your thoughts, and you'll be done. So that's the basics of glass. Questions about any of this stuff? It's like phase one. So in phase two here, we're going to pour the glass. I'll need 5 volunteers to help with some of the logistics up here. We'll describe that here in a moment. But this is hot enough that if I didn't have gloves and reflective suit on, yes, this is what I get to look like, it would actually catch my lab coat on fire. And you might think I'm lying, but one year, you guys, is that really going to happen? We took a piece of paper, and you just hold the paper right here, and you have somebody open it a little bit, and it just like count 1, 2, and then it turns black and catches on fire. So it's a crazy amount of heat. It's real. So the gloves will be smoking, even though this is a non-smoking campus, when I pull out some of these compositions. So the workflow is I'll have the batch records over here, and I'm going to call out what each batch is made out of. So I'll need somebody to just kind of be here and be looking at the load diagram for the furnace so that I'm coordinated on which batch I'm pulling out. You just start A, B, C, D, E, F, G, H, I, J, K. So that's one job. The second job is someone to do the door duty. And so you basically, this is a spring tensioned door. You just kind of hold here. You may want to wear a glove. I've got various gloves, and you just kind of get used to the way this door works. It's fairly little force, but you're kind of pulling out and it rocks up. And so the force is basically this way, but it makes it go up. And so you probably wear a glove and just be careful about the heat. And that way, as soon as I'm clear of the furnace, you carefully reclose that to hold the heat in. Otherwise, we'll be bleeding heat too much, and it causes the glass to start hardening, thickening up, because our pour temperatures get less and less. So that's the door. So then I'll be here pouring the glass, and I'll need someone to operate a torch. That's the most, I don't know if you want to say, cool, exciting, dangerous. So if you've done propane torch work or soldering, it's that same type of torch, just has a bigger tank. And this one's a little tricky. You have to pull slowly. It's like you have to add gas and then it sparks. If you pull too quick, then it doesn't always work, but slow pull. And the way that you will operate this is that if the glass disc is being poured here, you light and then move in from the side. There's a strand of glass. I'm not going to flame my finger here, but you will be heating that strand of glass about an inch away from the tip of the torch to keep that the hottest part, because we want to prevent stringing glass everywhere, which can happen. So that also helps me separate the crucible from the disc of glass. As soon as I pull the glass away, you then take that torch and come on now, you can do it. And then you'll be torching the surface of that glass about an inch away. And that's going to fire polish and get any imperfections from the pour to just kind of sink into that glass until it's nice and smooth like a perfect little disc. And the hottest part of the flame is that you'll see 4 bright blue inner flames right at that tip of that level of the inner flame. And I don't know if I need to clean this thing out, but my piezo is not working here. This is a piezoelectric fire starter spark. Nothing lasts these days. So, torch. Next up, you also get to be close and personal with the glass, the stamp. To keep all these batches straight, year after year, you're going to take these little dies that can be used for metals or leather, wood. I've put these on a lot of different things. But the problem is it's going to be backwards. And so it's going to look like backward 2A. And the way I test that is I line them up by pushing it on my finger here, and you can see a momentary indentation. You know, don't push too hard. You're branded for life. You can see what it's going to look like when you stamp the glass. And so once you get that lined up, let's say this was the glass. It's bright. It then fades to an orange color, and I'm like, okay, let's stamp it. You'll just take this and push it gently in the bottom so that it's a disc with an indentation of a letter and a number, and that gives us, it's A2 in this case, composition A 2022. And if it's spring, it would be 2A. If it's fall, it's A2. See what I did there? Yeah? So that way, with only 2 letters, we can document every decade of glass. So, stamp. It often is necessary to wear a glove to just give you a little bit of thermal shielding. Believe it or not, the radiant heat is pretty wicked on some of these. So you kind of move in, push. That's all it takes. But having one of those blue gloves helps knock down on some of that heat. That's the first die set for composition A2 that would be needed. And before I get the volunteers, last but not least, the firemen. I've never had to use the firemen, but Dr. Ray comes up with contingency plans. You know, I've done this with, well, it's got to be over 1,000, between 1,000 and 2,000 stout engineers over the last 12 years. So we've done this a lot. I've tried to engineer as much safety as I could into this, but eventually something could happen. So this is a carbon dioxide fire extinguisher, and people are real squeamish about fire extinguishers in an official capacity. They're like, I love this one. I think I may have already mentioned it. So in the event of a fire, we don't want you to fight the fire. We want you to calmly leave the building. Well, what if the fire is blocking the exit? We don't want you to fight the fire. We just want you to calmly exit the building. Well, what if a student is on fire? We don't want you to fight the fire. We just want you to calmly exit. So it's like a broken record, you know. So fire extinguisher training, it's really difficult. It's the word pass. I'm not going to squeeze this, but you pull the pin. You aim at the base of the flame. Not the flame itself, the base of the flame. Aim. Pull the pin. P, A, aim. Squeeze. And sweep side to side. PASS. Fire extinguisher training. Really hard, right? Now you've been certified, but that's the reason that they take a lot of fire extinguishers like, well, We don't want to have fire extinguishers everywhere because OSHA doesn't require it and because we don't give fire extinguisher training. Well, now you've been trained. I have had fire extinguisher training, can't you tell? So anyway, so that's the job list. The rest of us would probably just want to be on this side. We all have to wear safety goggles because it's unpredictable. But let's go ahead and get the volunteers. So could somebody help with the logistics? Thank you. Next up, we've got the door. So who wants to be up close and personal with operating the door? Anybody? Any volunteers? All right, thank you. So then the torch. All right, thank you. We got the torch covered, and so we will need safety goggles. Everybody. So then we've got the stamp. Any takers on the stamp? You want to do it? Okay. And then finally, you don't have to, I had one guy, he was a fireman, and right at the beginning, he already had it ready. You really don't have to do that. You don't even really have to hold it. It's here, and in the event something goes sideways, you're just there to, like, you know, hose flaming Dr. Ray down as he's rolling around the floor. So, all right, thanks.
I could just do them both.
Yeah, it doesn't matter. It's like I said, it's never came to that, but someday it might. So, all right, so I'm going to readjust the camera quick, and then we'll proceed. Right, so for the door, you know, I've got another set of welding gloves in my office, but these also would work fine. So if you just get used to the way these feel, this, maybe just one, maybe two, let's try those out. So we'll zoom in on the metal stage here. And so once we pour the glass, we will then be having to wait because it'll be really hot. You could actually cook on this surface once we're done with it. And so we'll be watching a couple of different videos while it cools on glass and the two different ways that you can think of the glass industry artistically or as a manufacturing process. And then once all that's done, we can move in and do our measurements. And then after some measurements, we'll also be able to use this little light table here to view the internal stress field of the glass. This looks like magic, but it's not magic. These are cross polarizers. And so when they're held parallel, it doesn't look like anything but just regular plastic. But when they're held perpendicular, notice I can turn my face on and off, right? Can you see that? Looks like magic, but it's not magic, it's science, obviously, but these are only allowing vertical polarization of light. Well, vertical, nothing cancels, but now it's vertical horizontal and it cancels everything. The cool thing about that is if you put that on a light table in a cross-polarized format, what you put between will have all these crazy colors based on how it polarizes light. And it turns out that glass and plastic and anything that's clear can polarize light if it has an internal stress field. And so you can see the result of the internal stress field by putting the glass on that cross polarizer stage there. So we'll take a look at that. It'll probably be an hour from now, but after a little while.
What gloves did you say to use for stamping?
I would probably just grab a pair of the nitrile gloves, yeah. All right. And the torch work sometimes gets a little toasty as well, so there are some welding gloves. Those thermal gloves are a little hard to control. So all right, now I feel safe. So yeah, it's pretty much the same as casting. So Now, I think we're in pretty good shape at this point. So most of the action will happen here. We'll just be pouring 11 discs. One thing to keep in mind with the torch is that what we've seen is that when you're doing a particular row, the flame from one will hit the previous piece of glass, and that's usually not a problem. So we're going to do one, or A, B, C, D, E, F. Well, by the time we get here to E, or F, if you're holding the torch at an angle like this and the flame is hitting the previously cast glass, it can actually cause it to side crack or spall off the side. So try to angle the flame so that you're always pointed either in the direction that we just went or even back a little bit so that you're keeping the flame off of the previous row. That's sort of a guiding principle here. It does make the glass a little more stable. And if it cracks a little bit, it's no big deal. But in general, try to keep that angle controlled. So yeah, it's no big deal. You just have to plan ahead. So all right, so this first glass is Silica Beach Sands. This is the Lake Michigan sand. We've got some 2.5 aluminum oxide, grams of aluminum oxide, 50 grams sodium carbonate, 26.8 calcium carbonate, and 0.49 grams of copper oxide. So batch A, and we're pulling from the front left. All right, so here we go. Just kind of slow out, looks good. And you want to stand back on the other side here. And go ahead and start hitting that glass there. Now restart. Yeah, restart that again. It's getting stuck. There we go. Hit that a little closer, closer, closer. There we go. That's perfect. And now, go ahead and hit that spot right there and fire polish that till it goes down in. Get a little bit closer. That's good. Okay, you can stop there. All right, so right about there, we can go ahead and stamp bottom edge there. You can go in a little bit. Yeah, it starts hardening off pretty quick there. So I think that's good. It's probably all right. Let's see what we got there. Yeah, I can see it. It's sort of a shadowy A2, but it works. So as that's cooling down, once you get into that dark orange, that's about perfect. If it starts getting a little past that, because the viscosity is dramatically increasing as you go. There's also another interesting effect you can see on this one, and that is some copper mirroring. So this was copper. In the middle of this flame, there is carbon monoxide, just like we talked about with smelting. And the carbon monoxide is actually able to pull some of the oxygen from the oxide and donate electrons to copper. So we actually have some little metallic copper particles in the surface of the glass where the flame was kissing the surface there. So that's what this appearance is. And interestingly, it's such a thin layer, you can see it from the top, but when you hold this up eventually and look in the light, you won't even see that copper effect. It's a surface mirror effect. So kind of an interesting side note there. All right, so next up is B2. So this is also some Lake Michigan sand. And this has a Gertzley borate, about 10 grams, sodium carbonate, crushed limestone with some dolomite, and also 0.01 cobalt oxide. So this will also be a blue, but probably a bit darker in shade, but because it's 0.01, that's a fairly low amount. Will be kind of interesting. Also, we expect, based on the borate, a wider disc to be formed because that should lower the viscosity. I've also noticed with the borate, we get a little puff of smoke for some reason that comes off right at the beginning. I don't know if we'll see that this time. Probably we will because we're a bit hotter, but we'll pour that one right here. So let me just verify this is striking it right here. So this is a button that locks it into place like this. So that might have been what was happening. We got enough here, so. Seems like my striker is just striking out. Really reliable, huh? So just try to go straight. You just got to keep restriking. And once you get that restruck, that's when you just move in. And at the beginning, it's sort of a top to bottom from the crucible down to the glass surface, top to bottom, working that bead of glass. And then once you come in, you're going to be hitting pretty concentrated right on the spot where it separated. So that's sort of the posture. But yeah, that one's getting a little unpredictable. So anyway, B2, pulling from front right. So a little closer. There you go. And then hit that top part till it's nice and smooth. All right, looks good. All right, that's fine. You can go ahead and push in. That's good. All right, so that's kind of how it goes. And I definitely can tell the difference with the borate. You see how much bigger that disc is? And the bead of glass that was being poured from the crucible looked distinctly thinner. So that's telling the story. Quick word on this stuff here. Fiberglass, it's very insidious. It looks like it's just a little needle of glass, but the problem is it can break, and if you start to bend it, when it bends straight, it can poke right in your finger. That has happened. There was a professor before my time that actually got a piece embedded in their skin and had to be surgically removed because it was at a spot that was always tickling a nerve inside their finger. So in general, don't touch fiberglass. I'll be breaking this off, putting it in the glass bin. It's not like fiberglass insulation where it's so thin it can't poke you as much. This stuff can actually get you. You're also hearing what's called crazing. Every time you hear that sound, a new little crack is forming in the glass that's residual on the inside of the crucible. The reason for that is differential shrink rate. So the coefficient of thermal expansion of the ceramic is different than the coefficient of thermal expansion of the glass. And so as that crucible is shrinking and the glass is also shrinking, you'll get these tension fields in the glass, and that is relieved by breaking the glass. And so we will hear eventually a chorus of crazing that'll be occurring there. And for those of you that are, happen to be up here, and you can feel free to stand up here if you want to get a little closer, you can actually see the cracks forming if you know where to look. So, all right, so next up is C2. And that cobalt, it's not looking terribly blue at the moment. It's looking more
Green.
Yeah, so I'm wondering if the iron from that sand and the low cobalt, because that's not the typical iron color and it's not the typical cobalt color. I think we're piggybacking the native impurity of the iron plus cobalt. That's actually kind of unexpected. So anyway, C2, that's Mason sand, so that's a fairly high impure sand. They're like little pebbles, dark pebbles in that one. It's 40 grams Mason sand, 52 grams of a high purity granusil, high silica sand. So it's going to be medium impurity there for that combo. 47 sodium carbonate, 25 crushed limestone with 0.09 chrome oxide. We're pulling from the middle. That chrome oxide should make it look green eventually. But chrome in particular does this interesting thing where it starts brown and then flashes to green at around 400 or 500 degrees Celsius. So it'll start one color and then fade to green, and then the green locks in. So that's what I was talking about. So that's what it looks like when glass shatters. As you can see, it's kind of unpredictable. Yeah, I'm going to sweep that up quick.
That was A2, wasn't it?
That was A2. So, well, the good news is that, you know, it's captured on video, and in theory this could be remelted, but I'll put this in a beaker so we can check the color. Yeah, just a little bit of super glue and a little bit of time. Come on. I saw some bubbles in this one that I was a little bit concerned about, but that was kind of early, so might be an exciting day. What's the worst that could happen? Yes, that one actually went pretty far. So, yeah, I'll put this in a beaker. The biggest thing is, you know, make sure there's no shards on you and you're not going to get cut. I don't think we have any complications there, but you also have to get this completely clean from those shards, otherwise they end up in other people's samples. So I think that's everybody's. So let me put this in a beaker quick. Glass plus a little bit of floor dirt there. Yeah, it is a nice,
Pretty.
a nice blue color. So we will eventually label that one to be A2. And I guess I've got a Sharpie hiding somewhere in here. So it's a good idea to, you know, hide Sharpies in your clothes in case you're ever held captive and you need to write on something. So there you go. Dr. Ray will never be able to, nobody will ever prevent me from writing my final memoir. You know, we got it covered here. So, okay. D2. C2. Oh, that's right, I was about to pour C2 when all the excitement happened. So this is the Mason sand with chrome. So, all right, we'll pour it in the same spot. So we'll be targeting right there and try to angle the flame a little bit away from this one. So maybe at an angle about like that for now. All right, let's do this. A little bit closer with that, that's good. Yeah, that's probably pretty good right there. And maybe wait just a second. Yeah, right about there. And you can go a little bit further into the disc, that's fine for now, but you can go a little bit higher, it makes it a bit easier. It also helps stabilize the glass if you're in maybe not quite a 1/4 inch, but just around off the edge a little bit. Yeah. So we'll see how long it takes for this to get to its final color here. It's a fairly low concentration, it looks like, but it starts off, like I said, kind of a brownish green. and ends up being a darker green. But this also has iron present, so it could also be tilted a little bit in color, but definitely looks brown to me right now. So we'll go ahead and I guess imagine that one's not there for now, and we'll pour the next one right here. So that was C. Next up is D2, or D2. Somebody happen to have the paper for D2? Or is this just going to be the mystery batch? D2? The paper? Do you remember what you put in? Was that you?
Yeah, it was me.
Okay.
Yeah. Yeah.
Okay, so take it.
Here, let me look at that.
Okay. If you just remember like the color in general, I never found D2,
it's
so.
purple.
Okay, so you
We
manganese?
need, manganese, yeah, and calcium carbonate, sodium carbonate, yeah, and the silica beach sand.
Oh, you use the Michigan sand again? Okay.
Yep.
Nice. So it sounds like it's a fairly straight batch with Michigan sand plus manganese dioxide. And do you happen to remember if it was high or low on the scale for manganese?
We went conservative with the manganese. It was
Down at the bottom there.
It was like 0.15.
0.15? Okay. So about a medium load of manganese, which should be purple. So perfect. That's all we needed. Yeah, we'll pour from the left, and we'll be pouring right there. I didn't know whose batch it was. That's
Yeah.
flying blind there. So, all right, D2. All right, I think that looks pretty good. So you can go ahead and stamp it. All right. As long as it stays under there, we're fine. I don't think anybody's wearing flip-flops in here. This is a really bad day to wear flip-flops. All right, so we'll pour the next one here. And the next batch is E2. We'll pour from the right, and E2, Mason sand, washing soda, crushed limestone. Is that it? No colorant? For E2, does that sound normal? Okay, so this is going to be the native color. And this one's going to be kind of cool because this is going to have some color because of the Mason sand, but this is going to be all native color from the raw mineral. So this will be kind of neat. This is an impure sand and an impure limestone. So it's iron plus mystery mineral from the sand. So E2. All right. Maybe angle it a little bit more toward me. That's good. Yeah, try to hit that so it sinks down in. We're getting close, but I still see a little bit of a, okay, I think that's good. Get that bump down in. Yeah, I think that's probably fine. All right. Oh,
Oh, are you okay?
good.
Which one was that?
I don't know.
Looked like it came
Oh,
off
it
that
was-
one.
It was my own.
Was that a side spall? Okay,
Yeah.
so that was, just checking you out. I don't
Yeah.
think I see any extra
No.
glass on you, but that came right, actually you got a little piece right here, so. It's tiny, so I'm not sure, but there is a little piece there. So this is an exciting day here. We'll put those pieces there. So that was probably due to some extra heat from the torch. It heated up that side more than the other side, and that caused it to spall off. So we'll try to angle that. It might be, if you can take this and just kind of tilt it, you can angle your flame so that you're always shooting kind of in this, either parallel or in this direction. So, yeah, it happens. This is, like I said, kind of unpredictable. And I'm wondering if this beach sand in particular is making it a little more, maybe. Yeah, I was looking for this brush here. Let me grab that. Yeah, these are exploding pancakes, right? All right. I think we're in good shape then. And you didn't get hit with any place that's bothering you, right? So I think most of it just kind of went
Most of it
out.
went like, it hit like.
Yeah, but I saw a field of glass shards in the air there, and you were kind of like right in the middle of them. So, all right, so we'll cast here, and I think that if we angle back this way, so I'm going to move these crucibles, give them more real estate on the back end here. That way you can kind of angle back, since more temperamental today. So F2. So again, it's the Michigan sand, 90 grams, washing soda, 53 grams, crushed limestone, another chrome oxide, 0.14 grams. So it seems like we'll be lots of shades of green here today, but yeah, angle back that way, I think we should be in good shape. So pulling from the middle, F2. Yep, looks good. Okay. So we'll let that one cool here a moment. You'll have a little more room on this next one because we'll be on the new row. So that was another chrome glass. We'll put the next one right here. The next one is composition G. So this is a Fisher silica. I think this might be our first example of a high purity silica. So Fisher silica, sodium carbonate, calcium carbonate, 5226, pretty standard. Slightly higher on the flux loading, just a little bit. And 0.1 grams of manganese. So this one, because we're using the pure silica, should hopefully be our truest purple color, since there's not a lot of iron. So we'll keep an eye on that, see when that color finally, in the glass industry they call it the striking temperature of the glass. The final temperature hits at a certain temperature. So, all right, so G2.
Yeah.
somewhere around there should be good. All right. So you can also tell on the strings of glass kind of what the final color will be. This one's kind of a, at the moment, kind of pinkish purple looking in color. And that one is a little bit larger diameter. Yeah, there is a final purple color fading in now. So pour the next one right there, try to angle back this way. Maybe we'll, yeah, we'll move the crucible over here, even though it's a little toasty yet. Give you some room on the backside there. So, okay, next up we have H2. And this one is 85 grams of mason sand, 50 grams sodium carbonate, 30 calcium carbonate, and this is 0.1 chrome. And this one used the clarifier, the 1 gram of sodium sulfate. And so for this one, we'll see if we see a big difference in bubbles. Like some of these, you'll definitely see more bubbles than others. This one is actually really clear. This one in particular has quite a few what appear to be little bubbles inside. So we'll see if it appears that the clarifier helped to remove bubbles. But mason sand plus chrome. So H2. Go ahead. Hold on a second. Actually, I need to push this back in. So go ahead. All right, looks good. Okay, so yeah, what happened there was apparently there was a little something. I don't know if there's a little bit of glass on the shelf, but it pulled the refractory brick a little too far, pulled the brick forward a little bit, and I was concerned it was going to conflict with the door shutting. So I had to push that in quick so it didn't create a snag with the door. I think we're fine, but the floor of this gets messed up, so I do re-brick it every once in a while. I build up a layer of refractory brick and then a really thin layer that's easy to change out so that if anything gets spilled on it, it melts in to the floor, makes it kind of sticky and messy. So only at high temperature though. So anyway, I think we're good. So that's the chrome. Next up, we'll put composition I, mason sand, washing soda, calcium carbonate with copper, 0.27 grams. So that's a medium-high copper with some of the iron impurity from the mason sand. Should be in the blue, but blue to green. So we'll put the next one right here, maybe kind of angled this way. Is that going to be in your way, or you think? I'll move it. So try to keep it a little safer. So, and you're going to try from that angle?
Yep.
Okay. So I2, yep, let's go ahead. Yep, looks good. All right, so for this next piece, we will probably need to, we got 2 more batches, so we'll move those back back here. So we'll probably just pour here and here. That work for you?
Sure.
Okay. So we can see more of that copper mirror effect, a little bit of a modeling I can see fading in there.
That one might blow up. Should be first.
No, I mean, the copper isn't presumably why the first one set off like that. You sometimes just never know. But it's not the metal inclusion that caused the first one to go. But we'll put that next one here. The next one is J2. Thank you. So maybe a slower, maybe try slow pull. So gas and then click for the spark. I don't know. Time to replace it. Okay, you can. So silica beach sand, Gersley borate. So the borate, this will make it lower viscosity. Washing soda limestone, cobalt sodium sulfate. So 0.01 cobalt. Should be a dark blue. We'll see. So composition J2. Okay. All right, I think it looks good. Okay, so one more left. And we'll just go ahead and put that one all the way back here. So the final batch for this set, 80 grams mason sand, 5 grams of alumina. That tightens it up a little bit. 50 grams washing soda, 30 grams of dolomite. So that's a magnesium-calcium mix, stabilizer flux. 0.4 copper, 2.4 iron. So this is our first example of an intentional mix. Blue-green. Maybe a smaller diameter because of the alumina. We'll see. The final one, K2. All right. Uh-oh. There's a chunk that just came out. That's a bad sign.
Uh-oh.
So this is probably going to be an unhappy glass. Oh, no. Oh. Yeah, work on that as much as you can to pull it down in. All right. I think that's a goner. Whenever,
I'm gonna sink this.
yeah, whenever you see that degree of like chunkiness, that focuses force onto those regions where it's like inconsistently melted batch. I'm not sure what is doing it, but yeah, that one's going to have some, it's under a lot of pressure. So, and I think this is the one that has the artwork on the outside. So this is the happy crucible that has the little,
Oh.
that was the copper again.
I was right. I knew it.
So it wasn't even the one I was currently suspecting. So, okay. So as this continues to cool, and it's sort of like the 1812 overture over here, we'll have punctuated explosions, right? We can take a look at some videos. Thank you for risking it all, folks. Appreciate your bravery up here. Like I said, I've never had anybody get hurt under my watch, but it's not like there's not opportunities. So hopefully we can keep that record going. Just no day in the lab. Yeah. You know it's going to be serious when Dr. Ray is wearing a spacesuit. So, so this next piece, we're going to watch a video of Dale Chihuly. Anybody ever heard of Dale Chihuly? Probably not. Maybe you have. But he's the best well-known art glass guy on Earth. I guess I should clean up those shards here quick too. Yeah, we'll let you take your picture quick of that one. That one's like a spotted cow. It's going to blow up. I don't know. Keep your eye on that one, but not too close. If it's not too bad, sometimes we can piece these back together, but these all look like they're in pretty bad shape. It's like, what's the diameter of the...
Oh, you were right.
What's the diameter of the debris field? Yeah, we can piece that one back together, possibly. So... a little more unpredictable today. Gotta sweep that up quick before it hits me in the face. There's certain things that plastic dustpans aren't meant for. That glass is actually melting into the dustpan, so that's exciting. Okay, so we'll keep the camera on the glass so we can see what happens during the video, but yeah. But we can take a look at what you can do with this material. So this first one is definitely a retro video. It's probably from around 1998 to 2002 time frame. So there's definitely kind of this 90s feel to it. This is a piece for, I think, Travel TV, shot out of, or maybe Discovery, out of Washington State. Dale Chihuly, famous glass blower. He's a kind of interesting looking guy. He's got this eye patch and this, you know, kind of Bob Ross hairdo. I used to think that the glass occupation was somehow how he lost his eye, but no, it was a car accident. I've actually developed quite an appreciation for his work. He's like world renowned. He and his wife, I think, have some kind of foundation. Anyway, so you'll see him. You'll also see some other people in his what they call hot shop, and they're doing some crazy stuff with glass. So we'll watch that first. Then we'll watch how it's made on glass bottles, which kind of shows you the panorama of completely open form art glass, and then how you lock that down with a manufacturing operation. But on that one, it's the split-second timing. Like a bad day at the bottle factory would have to be just mayhem, blobs of glass flying everywhere. But they've got this equipment timed so that as the next blob is falling through the air into toward the bottle former, this one is finishing the process. It removes the finished bottle, the mold comes back together, and it slams that next piece of glass in. It's like, there's no room for error in that one. But so this will be about 10 or 15 minutes worth. The glass is probably going to be cool enough to touch around 11 o'clock-ish. The pieces that blow up you can touch easier. The smaller pieces cool off faster. But anyway, Dale Chihuly. Let's see what we can see here.
This is where Dale's work is made and where we conduct most of the business that he does. This is the hot shop where we have hot glass.
We first met Joe, who was telling us a little bit about why Seattle is so good for glass blowing, and it's because its climate is not too hot, not too cold.
Our glass is 2,150 degrees Fahrenheit, and that's the working temperature of the glass. In order to melt it, we put it on what's called high fire, and it goes up to 2,500 degrees to melt it. So we should take a trip to the furnace.
Okay.
That's
a statement I never really expected to hear.
Oh no.
We're going to take a trip.
This is one of Dale's grad students talking here.
Well, I'm going to gather this, what we call a little gather here, and the pipe kind of heats up as we stick it in the furnace there. Wow. So we have this little device to keep ourselves from burning ourselves on the pipe. Turn, and then you kind of let it fall on center. There you go. It cools off.
Yeah.
There you go. See? Natural, that's the right. Hang it down and it'll go down.
Is the burn unit nearby?
We have a little device over there that patches us into the fire department. Kind of come out,
Yeah.
and then you lift it on out of there. Okay, up and out.
Yeah, there you go. Keep turning.
Wow.
Good. Keep turning. Good. Right now.
There you go. There you go. Now this is the marver. This is what we call the marver, and now you are marvering. Marvering the glass.
Marver's just heavy metal.
Yep. Very good. Oh, and this is a good shot coming up here too. With this is what we call a roller wrap.
We'll return to Foster in just a second. Oh, they're applying the red to it? Right.
Yeah. And these rollers are offset, so the bubble moves down and the color goes on it.
It's like taffy.
Dale founded it.
Oh, he did?
Yeah.
Okay.
He was the founder of the school.
So is he like the main glass man in Seattle?
He's about the main glass man in the world.
Really?
Yeah.
I was going to school here at the University of Washington and was taking a degree in interior architecture. Started getting interested in glass, started melting glass, and one night I blew glass out of a little kiln. And then from there I decided I wanted to be a glass blower.
Well, what we're working on today are these wall pieces, okay? And what you see the dark bubble on the inside?
Yeah.
That's actually an air bubble with a thin layer of color. That Bennett right there is about to drop on to the pipe. We're going to just reheat it, shape it, and with my great team, we'll hopefully get it in the box.
So,
Open
just stay out of your way. Where should we be?
No, I don't want you to stay out of the way. I want you to get right in my. I'm going to actually have you help me a little bit here.
Martin works for me, but he also works on his own work and has his own exhibitions. And many of the glass blowers that have worked with me have gone on to develop their own careers. Some of them, like Martin's, stay around and still work for me. Others go out on their own entirely. But there are some, I don't know if anybody told you, but there's something like 50 glass shops now, glass furnace studios in the Seattle area.
It's not really glass blowing, it's more like glass shaping. Because there's a lot of prep work into shaping the bubble and very little blowing. Okay,
Well, glass blowing is difficult to get started in because you have to have the equipment.
a little further.
So you've got an initial outlay of, a couple $100,000 to have a small glass shop, and then to run it costs a couple $1,000 a day.
Actually, what you're gonna do is, these are wooden paddles and they're to protect me from the heat.
Okay.
All right?
Teamwork. Hey, you guys are awesome.
So a couple things to watch here. What he's holding in his hand is a folded up piece of wet newspaper. Surprisingly, wet newspaper allows you to smooth and shape glass, and it boils off and steams away water, and it actually protects you on the other side of just that, you know, inch pad of wet newspaper. But the radiant heat, like what we felt here, are what is like killing him, because it's hitting any flat surface parallel to the glass. And so it's like his chin is about to get burnt off here, and they're basically just casting a shadow with this paddle for the heat. Now, he also mentioned the box. We're gonna get it in the box. What's that mean? Well, this is hot glass that still has lots of this tension inside, and to make it stable, unlike what we're doing, we're cold quenching this glass on a piece of metal. We're just letting it chill to room temperature quickly. If you were to pour it and then immediately place it into another furnace that's at an annealing temperature, so if it melts at 1200, let's say we set another furnace to 800, maybe 700, so Celsius, away from that melt temperature, but still hot enough that the aluminum silicon bonds or the silicon oxygen silicon bonds that are stretched can then break and then join with something that's closer to it. It relieves that internal stress before it gets locked into this like extended posture. So it's really all about that summation of all those bond angles that leads to this tension. So by putting it into the annealing oven, which you'll see here at the end of this video, they break it off the pipe and they put it in this lower temperature annealing oven, then you're pretty much safe. But while they're working it, this type of thing can happen if your timing is wrong on trying to work the glass at the wrong temperature. So they, of course, deal with shattering as well, but none of that happens in this video.
Oh, wow. I can't believe you can even talk. Turn.
Cap. Oh my gosh.
Should I be up there for you?
Wow.
You can shift a
Blow?
little bit, but don't
Yeah,
shift
shoot my chin. Stop blowing. All right, good. Level. Tip up. Right here. Don't stop. I'm right there.
This climate is conducive to glass blowing because it's not too hot. You know, the only really bad climate for a glass blower is a hot one.
When you blow glass, you blow the bottom of the vessel first, and now we're gonna break it off the blowpipe. Okay, pull. Glass always breaks at the coldest spot, right? So just a little drop of water here, drop of water there.
Yes.
Boom.
Wow, there it is.
Is that cool?
What you saw down there was those techniques have been used for.
So can you tell what color this is? It's kind of purple. And you know what metal that is? Manganese. This is manganese glass. You can tell just by looking at it. You'll notice that we have a piece over there that has the proper color characteristic to see it's almost similar concentration to what they're using.
2,000 years.
Squeeze it against you get in. Good. Now push down. Okay. Good. Hit the lip pad with one paddle. Good, man. You are on the ball.
That was great.
I'm just pushing down.
Push
I
harder.
can't even see
Push
it.
harder now.
Yes.
Ease into it. Push harder. Push. Let them open up. Good. Push, 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 push. All right. Now, when it starts to feel like it's not moving anymore, you're done. We've got as much work on that heat as we could. Now, come out. Good job.
Whoa! These
And
were
these
on
things-
fire.
And
That
so
was
is
good.
the
Full heat, Paul. All right. I'll take those.
Okay.
So
How
we
was
got-
that?
That was good. We got about 2 heats left.
Okay.
What we're doing now is we're going to peel this ball open flat to make the wall piece.
So this is not normal manufacturing at this point. That's definitely art there. So that's the annealing oven right there.
All right, so these are coolers, Mark?
Here, well, yeah, essentially their ovens are 900 degrees. The timing is just critical on that because you've got about, while it's heating, that all the work you all were doing comes down to that very last heat. That's where the shape is made. That's where the beauty happens. That's where the nuance, the delicacy of the whole piece. All that work is just for that one heat. And then in a few seconds, you come over here, and if your timing's off, crash, it falls on the floor. Where do you get your inspiration from?
I'm lucky in that the ideas come to me. You know, I probably don't run out of ideas. You know, sometimes you wonder if you run out of good ideas. Glass is a lot like water. You know, there's a lot of, I like water, I like glass, I like ice. There's a lot of characteristics. And it also kind of works like the ocean, makes forms like the, you know, there's some connection between all of that. Mm-hmm. So I end up blowing glass and stuff, everything. Half the stuff I make looks like it comes out of the ocean, mm-hmm. even if you don't want it to. I like the rain. It's really, I find it conducive to thinking. And I always tell people, if you had to write a book, you want to go to the Caribbean to write the book, or you want to go to Ireland, which is a lot rainier than Seattle. And where they're going to write the best book, even most people admit it's going to probably be Ireland. Somebody is an aspiring glassblower, where do they want to go? They want to move to Seattle, because here we've got, you know, more glass activity than anywhere else. I mean, Venice has more glass factories and furnaces in Seattle, but they're second to Venice. And I think I would be proud to say that we probably have more glass artists.
All right, so obviously, remember, properties, performance, cost, aesthetics, and style, so definitely scores higher on the aesthetics and style points. I did have a student that, I think it was just this past year, it might have been the year before, but we did this. He went on some vacation down to Smithsonian, Washington, D.C., and was like, they had this huge display of who? Guess who? Dale Chihuly. And he's like, after having that as sort of like prep work, we talked about this. He's like, I was able to see this in a whole different way, thinking about the color and the shape and how hard it would be. So this guy, with his appreciation of aesthetics and style, has made millions of dollars. He's a, you know, world known for this type of thing, the medium of glass, crazy colors, crazy shapes. So he's got my respect for being able to control all this. So that's Dale Chihuly. Now this next piece is probably more my wheelhouse, glass bottle fabrication, right? Sounds exciting. The way to view this is that there's a giant glass furnace up on like the ground floor, and then all this factory is built in the basement. And so there's basically a giant pool of glass with tapping spots on the bottom. And what you'll see is dripping this glass through by gravity, and then it will pinch these blobs of glass, which then fall through dies. They use gravity, really smart the way they got this set up. So as the glass falls through dies, it's sort of like the way you draw a wire through dies. They've got larger and smaller dies, so it funnels it into the right shape. It then goes to this thing called the scoot that looks a lot like something out of Star Wars for some reason, with all this, you know, robotic stuff with this hot glass flying through it. And that is partitioning it to maybe 20 different bottle formers. But keep your eye on the timing as they're making their preform, putting it into a blow mold, blowing it into the bottle, moving it on the hot conveyor to go off to the annealing oven or the annealing leer. The timing, as soon as they remove it from the Parison mold, it slams shut and plop goes in the next glass. Crazy. But the same features, you'll see annealing, stress cracking, but now in something mass-produced and more practical glass bottles. So might be a political ad here, we'll see. Yep, we knew it. Oh, this is a bad one.
Glass is made of natural ingredients that are abundant. Making it uses less energy than producing metal or plastic, and it can be endlessly recycled. Whether they're coloured or clear then, glass bottles and jars are always green. The recipe for glass combines several natural raw materials. The main ones are silica sand, soda ash, and limestone. Silica sand usually makes up about 45% of the batch. The soda ash helps melt the silica evenly. It makes up about 15%. A limestone content of about 10% makes the finished glass more durable. These ingredients are combined with recycled glass called cullet. The factory's equipment feeds precise amounts of the materials into a furnace. After 24 hours at 1500 degrees Celsius, a gooey liquid that's the consistency of honey is produced. The molten glass pours out of the furnace. Shears cut the flow at precise intervals to produce cylindrical globs. Each glob is the exact amount required to make up one bottle or jar. They drop to a device called the scoop. The scoop moves them to troughs that feed them to jar forming and bottle forming machines. A glob of molten glass goes into a preliminary mold. Matter of seconds, it comes out as a miniature version of the bottle, known as a parison. Each parison then moves into a blow mold, the cavity of which is the shape of the final bottle. The equipment blows compressed air into the parison, stretching the glass outward towards the wall of the mold cavity. This process creates the final bottle shape and hollows out the inside. These are amber-coloured beer bottles. The colour is produced by adding small amounts of iron, sulphur and carbon to the glass mix. A similar manufacturing process is used to produce other types of bottles and jars. In this run, the company is making 375 milliliter wine bottles out of clear glass. This run is producing bottles also out of clear glass. This mold, though, has a special feature, a recessed insignia on one of the walls, which produces a raised insignia on the front of the bottle. After the bottles leave the forming machine, they travel through flames. Otherwise, they would cool down too quickly and crack from thermal shock. A loader now gently pushes the bottles into what's called an annealing layer. The bottles cool at a controlled rate as they move through the layer. This gradually releases the stress from the glass. As the bottles exit, they're sprayed with lubricant. This enables them to move smoothly through the rest of the inspection and packaging line. The bottles now single file to head into the automatic inspection station. As the machine spins each bottle, cameras and probes check for imperfections such as cracks or bubbles. The inspection equipment then examines the top to check dimensions and ensure the threads for the screw cap are molded correctly. Before shipping, each bottle gets a final visual inspection.
Great internship position there,
The
right?
proportion of cullet in glass can be as high as 90%. Cullet melts at a lower temperature, so for every 10% of cullet in the mix, the factory uses up to 2.5% less energy to produce its glass. Now that is a clear incentive to recycle.
All right, so there we have it. The artistic side, the practical side of glass. I did have a student that said that his dad worked at a place like this. He was an electrician. He said only briefly, though. He said that he worked on some of that optical sensing equipment that could tell where the glass was and how it was moving around. And he said that this place didn't like to shut down to do repairs. So he said that they would be fixing sensors while it's running. And he says that there was this is the student's description. It's one time when he's working on this shoot and the glass is going like right in front of his face and he's rewiring the sensor. And so at the lunchtime, he's asking the old timers, been there for years, how do you do this without hurting yourself? And he said that they all went, well, you do hurt yourself. And they all had these like horrible burns from accidents that had happened when they're doing this. And so he said his dad decided that wasn't the job for him and moved on, but crazy. All right, so let's see. Only slightly painful, that's progress. So what we'll probably do here is we can go ahead and do some preliminary measurements. Like I said, don't touch the broken shards, don't touch fiberglass. It's bad. Definitely wear your goggles. But things are stabilizing up here now. But if I were to handle them now, I could still make a cold spot, and it still could possibly shatter. But we can go ahead and take some ruler length measurements on the ones that survived. And once we get a little bit cooler, we'll move it over here to the light table and look at internal stress fields. And you can take pictures of all this, obviously, too. But there are rulers over there, and so feel free to grab that, start getting your preliminary measurements, and I'll let you know when we can move them over for the full inspection. Oh, you'll still want to take measurements of the whole group. Everyone's gonna report everyone else's glass, and for this, we're not gonna know the diameter, but we can approximate the viscosity during the pour based on the others, based on the video. And also, if you want to just check out the light table to see what internal stress looks like, we'll put plastic parts on here to begin with, just so you can see how you can see internal stress in plastic, just like you can in glass. You got to look from the top. And there could be some glass shards on the floor, so do still be a bit careful. So here's the moment we lost the blue one on screen here. Yeah, I mean, this is posted. So right there, you can see what internal stress looks like. What's kind of spooky about it is like, where is the force coming from? How does it do that? Well, the answer is it's in the bonds. They're like a billion little springs. And if they're all slightly loaded, all that can relieve, and that energy comes from stored spring energy in the bonds during internal stress. So it's really surprising. So there's the videos on Prince Rupert's drops will actually dig into some of that. But yeah, you can also see the you see the reaction time. Watch so right there. Well, no, you could totally figure out reaction times with that based on milliseconds, right? So.
Where's the one that shattered on?
So was this the one?
It was one. It was either.
I think it was the one right on the end.
I
So-
think it was the one right on the end. Maybe. Either that
No,
one
I
or-
think it was that
no,
one.
yeah, it was that one.
Because we said it.
See, I think it's this one because you can see how the heat's hitting it.
Yeah.
Yeah, so watch as the stamp moves in, you're going to see it, and it came off of this edge.
Yeah.
That edge, what's called spalling, and it's going to like create this. And there were some tiny little particles, and I think you might still have a little one, so be careful with that.
Okay.
Um,
So I always take a cold shower first
well,
when I get home.
you just had a little bit of a fine dust. Maybe it was nothing, but it's awful when you know what's about to happen, right? Well,
Yeah,
There.
there it is.
there it was. Yeah. It happened a little bit later than I thought I remember, but
Oh yeah, I guess it was.
right there. But those were little pieces, and man, they just kind of went everywhere.
You're holding there too long. Gotta get it.
But hey, we all have nerves of steel. Nobody overreacted. That's good. So there's the one in the back corner that went. Okay, yeah, it's no big deal as long as we kind of can piece back together what it was. I wondered if that one was still in the lab or something when nobody had turned it in. So I'm not.
Yeah.
I don't know.
It's perfectly possible. It winded up in the trash.
Oh, okay.
I may have just.
Well, maybe if we don't find it, we kind of have a couple options. So you could approximate,
Yeah, that'd be.
and that might get us part of the way there, and that way we can actually put a batch in the an approximate in the spreadsheet,
Okay.
and that way I'll have a record to know what to put in.
I have a general idea.
Okay, excellent. So we'll add that to the mix here.
Do we
So,
need that information for our?
yeah, I'm going to take a picture of it to PDF it, and then we'll give it right back. Yeah, you can take them. So I got it. So we'll add that to the spreadsheet. So this one is like yellow. Still a little bit toasty.
Said that, hey, we didn't get, I said we could have maybe put less liquid in to see if we have some
So fluxes can be lithium, that's the only flux we had, and then flux stable. So you've got calcium carbonate typically, sometimes it's mixed calcium, magnesium, carbonate, and dolomite. Both of those would add a little bit more strength and stability because of the divalent +2. So that's come up with a way to just benchmark it to 3, low, medium, high, benchmark it to 10, maybe say. High viscosity spreads less. So our lowest viscosity was probably this one that did a side shatter because that had the borate, so that one poured the easiest. And the one that was the smallest or tightest diameter probably the highest viscosity. So we've actually got a couple of them.
high viscosity spreads less.
Right, it's thick, so when it hits the surface, it stays in a taller stack. It doesn't spread out as much. The lower viscosity spreads and flattens. It's the right way to use it.
Oh, you just do my scale. Oh. So that would be.
Getting close on temperature. A couple more minutes and then we'll move it over and we'll go ahead and put these in a beaker.
I just hand wrote it in. Five is what it was this. Or one is most business, five. And you said you were. nice purple. The other one has like dark purple. Or no, it's like an amber color.
Yeah, that's. I just couldn't see it. Well, I hear you said it didn't, and somehow this all got saved.
I was hoping for that.
Get the whole family back together.
We're just making glasses.
It's our broken dreams. Speaker of broken dreams, shattered dreams. Right there.
Shattered dreams.
Welcome to Stout, shattered dreams. So, J2. Yeah, beakers for our shattered dreams.
Yeah, that's a cool one.
Yeah, that video is still being made. So this is at the Stout Materials live stream. It doesn't have a whole lot of viral videos, but lots of educational stuff. So if you follow the playlist, it's also on that parent channel.
Come on, we should have made an announcement that we were going to have exploding glass today.
I know. Well, you never quite know, but
Possibility of exploding glass.
there's definitely that.
We can end up moving it later.
Even though it's on the light table, it still can kind of shatter partially unexpectedly. So still wear your safety glasses and goggles and be careful. Still sharp hazards. So I'll probably do a little bit of filing quick on that one that has sharp edges. So now you can get your pictures of the polarization, so you can just sort of stand above this and just sort of look from the top, and what you'll see are bands of color and this kind of a gray and white middle area. The qualitative assessment is that the tighter the banding of color, the higher the internal stress field. So I'm going to put a little beaker here too. Those have been annealed. If you look at the beaker, all you'll see is gray color, and you won't see all those bands of color. So we'll add this remaining one once I file off the sharp edge here.
Yeah, that's such a
It's like, yeah. so
color.
sorry.
It's like red green color one.
Wait, you got a photo?
Yeah, I got it. I should have